So we had been talking about extrasolar planets or exoplanets, as they're more commonly called today. And we'd ended saying that what happens is that our best understanding is that in the um, Proplid, the nebula that's left over from the accretion disk of when a star formed, it's left over or orbiting around the young star or protostar, that things start clumping up. And as they start clumping up in there, you have little droplets, chondrules forming, sticking together. It's a very high temperature environment. It's very hot in there, and because you're basically squeezing gas together, and you got the protostar starting to shine, and it's bright and heating things up, and so these little molten droplets stick together, and as things cool off, they form rocks, chondrites. And eventually these things start clumping up, running into each other, and little ones hitting big ones, making things bigger. And then you have the planetesimals, a whole bunch of smallish to largish objects here that start to resemble small planets. And over time, as they're all orbiting around, however, they start running into each other, and what you end up with is a handful of leftover remnants that resembles the solar system. We found these chondritic meteorites, so we know that they're out there. And so there's a few that didn't get around to running into things, and so they're running into things now. And so we know these things are out there, and so this does give us reason to believe that this model is correct. The other interesting thing is that that would explain planets like Mercury, Venus, Earth, Mars, but what about the other planets? Well, as you get farther away from the protostar, the protosun, it gets cooler. And eventually, at some distance out here, you end up with what they call the snow line. At that distance, then it's cool enough that H2O, which is very common. Hydrogen obviously is one of those common things in the universe, and oxygen turns out to be a relatively frequent byproduct of star formation. So when stars die, or rather not star formation, but relatively frequent byproduct of nuclear fusion inside stars. So when stars die, it goes spewing out into space. And so what happens is that water is going to be one of the more common compounds that's out there. But up close to the protosun, it's too hot, and so you don't get water as part of the chondrites. But when you get farther outwards, then what happens is the water then can be solid. Well, that means that since this is a very common sort of thing, you could build more of these rocks that have water in them, and that can easily double or triple or more the amount of stuff that you have to build things out of, which means you can build bigger planets. In fact, if you build a big enough planet, it will have enough gravity to hold on to hydrogen and helium. That's two of the most common things in the universe. So if you have enough gravity to hold on to the most abundant stuff in the universe, you can build really big planets. So that would suggest in the outer solar system, you start building not just the sort of things you build in the inner solar system. Inner solar system, you're going to have these you're going to have the chondrites, and they're going to build rocky planetesimals. In the outer solar system, you can build icy planetesimals, which means you have more of them, and they can come together to build bigger planets that have more gravity, that can hold on to the lighter stuff, which means you now have these gas giants. In fact, the outer planets are characterized by gas giants, Uranus and Neptune. In fact, we believe Uranus and Neptune have a huge percentage of them is actually liquid water, and they're almost like ocean worlds at their cores, and that makes them much more mass than the inner planets, and that holds on to even more mass, which is hydrogen and helium. And so they become vastly larger worlds. And so we have gas giants in the outer solar system. And so this model that they came up with that they're working through the mathematics of actually seems to match what we see. Now remember, that's one of the hallmarks of a scientific model. It's not just a guess. They go through the mathematics as to how all this stuff would happen, and they say, well, does it predict, does the math of the model, the mathematics, then predict what we see? And in this case, it does. So that seems to work. So the inner solar system is going to be small rocky worlds. The outer solar system, giant gassy worlds. In fact, we call these gas giants out here. They are huge. You could fit 1,000 Earths inside of Jupiter. You could fit enormous, like hundreds of Earths inside of Uranus and Neptune. And so these are considerably larger worlds, and the bulk of them is hydrogen and helium. So this seems solid. It seems to explain what we see. There are some differences, though. It doesn't completely explain Jupiter or maybe even Saturn, which are almost all hydrogen and helium. They have a far lower percentage of other stuff than does Uranus and Neptune. In fact, Jupiter seems to have a composition very, very close to that of the Sun. So what happened there? Well, our idea is that maybe it actually forms very similar to the original idea, that you have the propelid, but then what happens is in the propelid, a bunch of gas just swirls for whatever reason, like a density wave passes through the propelid and makes a little piece of it extra dense. So it's almost as if it's exceeding a Jeans criterion type thing and clumps up to make a new object out here. That new object forming in a similar process to the way a star forms in the outer solar system, except it's not going to be big enough to be a star. It's not even big enough to be a brown dwarf. It totally failed in terms of making a star, but it's going to be mostly hydrogen and helium, and going to have some rocky stuff in it because there's going to be some rocky stuff in the propelid. And so that would give you something that looks like Jupiter and Saturn. And so those worlds may, in fact, have formed in a different way than Uranus and Neptune did, which raises a question. You know, a lot of people complain about Pluto being kicked off the list. Well, Pluto does not conform to these other things, which is why it was kicked off the list. But then if that's the case, then possibly Jupiter doesn't either. So maybe Jupiter should also be off the list. Maybe Jupiter should be a different kind of object than the rest of the planets. So just, you know, that's just another interesting sort of thing to consider. So our basic model, we have the cloud of gas, comes together, forms a protostar, swirling around the protostar to the accretion disk. As the protostar heats up, it stops the accretion disk from accreting, and you have this leftover disk of dust and ice and gas, and the dust and even the ice start clumping together to make little rocks. The little rocks come to clump together, make bigger things. Those bigger things left over, those bigger things would be asteroids and comets. And then what would happen is that something really big would form in there like Jupiter, and then the inner solar system, then what you'd have is you would have a whole bunch of planetesimals that start bumping into each other and congregating to make planets. In the outer solar system, you have icy planetesimals that allow you to make bigger planets, which then have enough gravity to suck in all the hydrogen and helium and make even bigger planets. And so that gives you the sort of thing that we have out there. Now, there's an interesting thing about this. As all the planets are going around the sun, we've got the sun, we got Jupiter, we have Saturn. We also have Uranus and Neptune, or most likely Neptune than Uranus. Now, what happens is that Jupiter and Saturn are orbiting here, but Jupiter is going to go around a little bit faster because it's closer to the sun. It's always going to get in front of Saturn. Gravity is going to pull back on Jupiter, pull forward on Saturn. So what's going to happen is, you can show this sort of mathematically, what's going to happen is Jupiter is going to spiral in closer to the sun, and Saturn is going to end up spiraling out farther from the sun. And so there's evidence, in fact, from looking at the compositions of Jupiter and Saturn, they probably formed closer to each other than they currently are. Now, when Jupiter moved inwards, it shut off planet formation in the inner solar system. And so a whole bunch of leftover planetesimals would end up congregating just inside Jupiter's orbit. Well, that'd be the asteroid belt. Now, when Saturn moved out, Saturn started pushing on Uranus and Neptune, causing Uranus to move a little bit out and causing Neptune to move way out. And so it's believed that Neptune actually originally formed closer to the Sun than Uranus. But when Jupiter and Saturn formed, it pushed them further out, and it pushed Neptune much further out than it did Uranus. Well, as they moved out, all the little icy planetesimals out here got kicked way out. Okay, and so that would mean there'd be a whole bunch of little icy planetesimals out there. Things kind of like in asteroids, but farther out. Remember, you can also get bigger things than regular asteroids because some of these things are going to be very, very icy. When we look out here, we see Pluto as this icy thing, and it's got this weird orbit that actually is super elliptical. It gets closer to the Sun than Neptune in places, and then much farther away in other places. It's also tilted relative to everything else. That's kind of the orbit you would expect if something got kicked out. And so it's believed that possibly that Pluto is one of these planetesimals or protoplanets that got kicked out. Now, when it got kicked off the list of planets, everybody thought this was like horrible, you know, because they learned it as part of the planets. I thought it was actually kind of interesting because it actually makes Pluto a more interesting object. It's not just a teeny tiny little planet. It's actually a remnant of the formation of the solar system. That means studying it is even more interesting than if it would just happen to be the smallest planet. And so I don't think it's any slight to Pluto at all. There are, in fact, a whole bunch of these things that are out here. Astronomer and Gerald Kuiper suggested that some of these things that we call comets come from a reservoir of objects like a big donut shape around the rest of the solar system, so we call them Kuiper belt objects. Eris is one of these. Eris is actually the thing that they found that kicked Pluto off the list because it turned out to be a tiny bit bigger than Pluto and had an orbit really weird like Pluto, had a chemical composition almost exactly like Pluto. And so the idea that if Pluto was a planet, then something exactly like Pluto except bigger would also be a planet. But then something exactly like Pluto but almost the same size as Pluto would also be a planet. So it'd be a whole bunch more planets. And as Jupiter and Saturn moved out, they probably also kicked a whole bunch of things really far out. And so there may have been a whole bunch of icy things that formed way out there. Some of them kicked out when Jupiter and Saturn moved out, and then some of them actually may be forming in the globule surrounding the young solar system. And so surrounding everything from Jan Oort came with the idea, and we call this the Oort cloud. And so there's actually two reservoirs of comets, a donut-shaped region out beyond the farthest planet, the Kuiper belt, and then the even further out is a big spherical sort of halo called the Oort cloud.